Well, we have learned in the previous section how to determine the resulting force from concurrent forces, that is, forces that intersect in the line of action at a common point. But how can the resulting force of two parallel forces be determined? In this example, two parallel forces F1 and F2 are shown. The trick here is to insert mutually cancelling auxiliary forces. We add the auxiliary force A at the origin of force F1. At the same time, we add the auxiliary force minus A to the other force F2. Since the two forces cancel each other out, the system is not affected. We can use these auxiliary forces for determination. With the two auxiliary forces, we can now draw a resultant force of F1 and A and a resultant force of F2 and minus A. Since we can always move the forces along the line of action on a rigid body, we now move the two resulting forces R1 and R2 to the point where they meet. With the parallelogram of forces, we can now determine the resulting force R. This resultant force is the resultant of the two parallel forces F1 and F2. We see that the resulting force is the sum of F1 and F2. If we define the distance between F1 and F2 as the width W and the perpendicular distance between the points of origin to the resulting force as length L, then we can divide the width W with the two lengths h1 and h2. From this we can deduce that h1 divided by L equals A divided by F1, and analogously h2 divided by L equals A divided by F2. This gives h1 times F1 equals h2 times F2. This principle is also known as the principle of the lever. We have now learned how to determine the resulting force of two parallel forces. But what do we do if the two parallel forces cancel each other out in their sum? Here in the example, two parallel forces are shown. One force, F1, points in an upward direction, while the other force points in a downward direction with the same magnitude. If we calculate the resulting force with R equal to F1 plus F2, we see that R is 0 and the forces cancel each other out. However, the forces still have an effect on the body. Instead of a translational effect, as we have had so far, these two forces have a rotational effect. In our example, the body would rotate clockwise. The two forces that cancel each other out are called couples. The rotational effect of the couple is called moment. This rotational effect can be compared to a car steering wheel. In this case, a couple also applies a torque to the steering wheel, either clockwise or counterclockwise. The moment is calculated by multiplying the force by the length. In our example, m would be equal to L times F1, or m would be equal to L times F2. Since F1 and F2 are equal in magnitude, both are the same result. The unit of moment is Newton meter. We know from the previous contents that a force on a rigid body can be shifted on its line of action. However, it can only move along its line of action and cannot deviate from it. The special feature of the moment is that it can be placed anywhere in the body at will. Here in the example, we have a couple with the magnitude F1. By adding the auxiliary force A, we can calculate a resulting force from F1 and A, which we now call F2. The two forces F2, which have the same magnitude, can now be moved along their line of action. The force F2 has increased compared to F1. But we also see that the distance L2 has decreased compared to L1. We can write that F1 times L1 is equal to F2 times L2. This principle can be carried out with an infinite number of different auxiliary forces A, and so we can determine an infinite number of couples of different lengths. The notation of the moment is not performed as a couple, but as a large M, with an arrow representing a rotational movement, either clockwise or counterclockwise, as shown in the example here. As already mentioned, the moment is calculated by the force times the length, so M equals F times L. Moments can also be added together. Here in the example are now two couples, which are replaced by M1 and M2 with the corresponding rotary arrows. Here we have a moment M1, which works clockwise, and a moment M2, which works counterclockwise. In statics, we consider moments which work counterclockwise as positive and moments which work clockwise as negative. So, the resulting moment Mr is Mr equal to minus M1 plus M2. So, Mr equals minus F1 times L1 plus F2 times L2. The resulting torque is therefore a sum of all torques. Since we always have an equilibrium in statics, the condition for this is that no rotational movement takes place. Therefore, we can formulate the equilibrium condition regarding moments. Mr equals the sum of all Mi equals 0. Let us now take the following example. We have a circular body with a point C in the middle, which is the center of the body. On the right side of the body, a force F now acts. Intuitively, we know that this force has a translational and also a rotational component on the body. To calculate these two components, we can use the following trick. First, we insert two auxiliary forces with the same magnitude as our force F at the point C. The two auxiliary forces cancel each other out, so this has no influence on our system and we are allowed to do so. Now we see that the two lower forces form a couple with the length L. We can now describe this couple as a moment M. We now see that at point C there is a counterclockwise moment and a force in the upward direction. The moment can be calculated as M equals F times L. Thus, we have determined the translational component, which is the force F, and the rotational component, which is the moment M. I want to use this opportunity to explain a few more terms. The superscript at the moment M, C, is the reference point. The length L between the line of action of the force F and the point C is called the lever arm. In this example, we have a body on which three forces act, F1, F2 and F3. These forces have a special property that their line of action intersects at one point, in this example the point 0. As we have already learned, such forces are called concurrent forces, and as we have already also learned, we know that these forces can be added by the force polygon. But how can forces be added which are not concurrent and which do not intersect in a point? To do this, we use the same procedure as in the previous slide. With the same magnitude as the force F1, we create two mutually cancelling auxiliary forces at point 0. Now we move the force F1 along its line of action. As we know from lesson 1, we can do this because the body is a rigid body. We now see that a couple with a distance L1 has formed. We can describe this couple as the moment M1. The same procedure applies now for F2. We form the two auxiliary forces at point 0 and move the force F2 along its line of action. Now we replace the couple by the moment M2. For F3, also the same procedure is applied. We form the auxiliaries and replace the couple with the moment M3. Now we have three concurrent forces at the point 0, F1, F2 and F3, and the three moments M1, M2 and M3. Since the forces are concurrent forces, we can now use the force polygon to form the resulting force. As we already know, we can arrange the force polygon in any order. So we can now draw the force F1, followed by the force F3, and finally the force F2. And thus, we have determined the resulting force Fr. Now we have to add the moments. For the resulting moment, we need the sum of all moments. So Mr equals M1 plus M2 plus M3. Since M1 is clockwise, its value is negative. M2 and M3 run counterclockwise, so they are positive. So we can now write Mr equals minus F1 times L1 plus F2 times L2 plus F3 times L3. So we added the three non-concurrent forces and replaced them with the resulting force and moment at the point 0. In this slide, I want to talk about the degrees of freedom. In the following example, we see a rectangular body. This body is two-dimensional and is located on the xy coordinate system. How can the body theoretically move on this coordinate system? The body can move in the direction of the x-axis. It can also move in the direction of the y-axis. Finally, it can also rotate on the xy plane. In this respect, it can also be said that the body rotates around the z-axis, which here goes into the depth. These three movement possibilities, the movement in the x-axis, the movement in the y-axis, and the rotation, result in the body having 3 degrees of freedom. Now that we know the 3 degrees of freedom, it follows that for an equilibrium all these 3 degrees of freedom must be 0. So the sum of all forces in x direction is 0, the sum of all forces in y direction is 0, and the sum of all moments around any point, here called point 0, is 0. However, the moments can also be formed not only around one point, but around 2 points. So only one condition of the force and 2 conditions of the moments are needed. So the sum of all forces in x direction is 0, the sum of all moments around point 0 is 0, and the sum of all moments around point 1 is 0. We then also have an equilibrium as in the first equation. The same is true if we calculate the sum of all forces in the y direction instead of the sum of all forces in the x direction. Finally, an equilibrium is also present if the moments around 3 different points are 0. So, the sum of all moments around point 0 is 0, the sum of all moments around point 1 is 0, and the sum of all moments around point 2 is 0. However, it must be noted that the 3 points 0, 1 and 2 must not be on the same line. We have learned how moments are formed in 2-dimensional space. But what about moments in 3-dimensional space? Here in the example, we have a force F1 on an xy plane in 2-dimensional space. We now want to find out the exerted moment of the force F1 in relation to point 0. As we have already learned in the previous sections, we know that this is an anti-clockwise movement with the equation m1 equals F1 times L1. If we now take a third axis, the z-axis, for the 3-dimensional space, we use a different notation of the moment. The moment of the force F1 is a moment rotating around the z-axis. The moment is positive if we look in the positive direction of the z-axis, and the moment moves clockwise. Or if we look in the negative direction of the z-axis, and the moment moves counterclockwise. In this case, the moment is positive, and we indicate this by drawing an arrow in the direction of the positive z-axis. With the difference to the force, At the moment, a double arrow is drawn at the end. The arrow direction can also be determined by using the right-hand rule. In vector notation, the moment is the cross product of F1 and L1. On a rigid body, the moment vector can be moved parallel to its line. The moment vector is a free vector.